Thanks for the introduction. Welcome everyone to the first presentation today. I'm going to talk about a little property, freedom from interference, that you often encounter in safety-related development. This is the outline of this talk. I'm going to introduce the feature, present our technology, the architecture check, and then proceed how to derive a partition architecture to prove this property of freedom from interference, discuss a little bit about if this is already the complete solution, and we're going to conclude in the end. It's the introduction. Well, the title of the slide says it all, use static analysis. When you're doing any safety-related development, you have to do a rigorous design of your software architecture and to enable the safety process and to assign safety requirements. And quite often you encounter, especially in automotive industry, looking at ISO 26262, you encounter the situation that you have to assign software elements of different safety levels, different ASILs, to the same hardware element. So they have to coexist on the same piece of hardware. And you need to enable this coexistence via this property of freedom from interference. I'm going to discuss a little bit more details on the next slide. However, the message here is there is static analysis that you can use to ensure this property exists quite early in the development process. And well, we want to encourage this should be used, and we want to highlight one way how to ensure this property. So freedom from interference is a property where you're looking at two safety elements, and one has a fault. It causes some failure, and you need to ensure that this failure does not propagate into another safety element and cause a dependent failure in that other element. For example, if you have an element A that is assigned a higher ASIL and another element has a lower ASIL, then you don't want the potential failure in a lower ASIL to propagate into your high quality piece of software, into your safe application. So in the safety standard, ISO 26262, different categories of faults are identified that may cause such cascading failures: timing and execution, memory or access to memory, and exchange of information. And we're looking particularly on the memory part, where one piece of one software element can access shared memory and may modify that. And if a safety function relies on the consistency of that memory state, it will cause a cascading failure. And that's one of the main properties where we can actually do something quite early in the development, and this presentation should show how to do that. So let me highlight this point. We want quite early in the development process to avoid these issues. So we're looking at a technology verification of software architecture. So if you follow this default V model for software development, you define software requirements early, you derive your software architecture, and start implementing units, software components. And then you go up via the verification. You're doing the unit verification, go over to integration and verifying the complete integrated product, and finally the software test. And any deviation that is discovered here will cause a lot of pain in your project, a lot of effort, because you have to go back into the requirement analysis and fix it. If you only discover issues in the integration phase, for example, if you activate an MPU, you will have to go back to the software architecture part somewhat. So the earlier you can discover an issue, the better for saving cost in the development and saving pain. And that's exactly where we want to go. We want to enable this loop here, so that as soon as you start implementing software, you get a feedback, well, this is this deviates from the architecture, so either the architecture is wrong or the implementation is wrong. And to enable such a architecture verification, of course, you need to have an architecture. And what do we as people from a company that does static analysis consider as an architecture? Well, it's basically the static architecture. It's the composition of software component elements and the relations between them. So I'm indicated here as single arcs between the software elements. Basically, this means this schedule element may access algo element. And what may access mean is, can be configured, of course. It can mean that it may access global memory, may call functions, may send data, something like that. And this can be presented in any form. Most customers use case tools like Enterprise Architect. You can import that model into the verification tool, or you can even use other tools. You can use textual representations to describe this architecture. This could even be generated completely from a single or small Python script. It doesn't matter how the technical architecture is described, you just need to have a formal description for this. And our idea is we interpret this architecture and then compare it to the source code that is actually implemented. So as the second ingredient for the architecture check, you need a representation of your source code. Basically, source code can be compiled, can be analyzed, and we can create an abstraction or an abstract view on the source code. And this is shown here on this picture. There are directories, source directory, application directory, application 1, basic software, and there are subdirectories for the individual modules, and you see even source code files inside of that. And you could drill deeper, as is shown here. This red square is used for a single function, a C function. But you can keep it at that level of abstraction that is suitable for comparison to the architecture. You just need to identify which part of the implementation belong to which part in the architecture model. And the dependencies shown here are derived from the static analysis tool. So here it was identified that some function in this source code file will call a function declared in this header file over there. And once you have those pieces, you have an architecture model, you have an implementation, representation, abstracted model of the actual implementation. You can do something like this because you can define the mapping. This implementation of inside of the algo directory implements exactly what is designed here in this architecture node algo. And we do that for all of the pieces in the architecture, and then we have a mapping from source code to the model. Then we want to do a check. Does this is this compliant, this implementation and that architecture model? So the checking algorithm proceeds roughly like this. We consider all dependencies in the abstracted source code model, map these onto the architecture model using the mapping shown on the previous slide, and then we check compliance between the two. So there may be, the result may be convergence. So there is a dependency in the implementation, and it's supposed to be there. So, whoa, this is good. We show a green edge convergent. Or we may have a dependency in the implementation, but that shouldn't be there according to the architecture. So it's a divergence. We show a red edge. And then once this part is finished, we consider all remaining dependencies in the architecture. And then there are two options. Either this dependency in the model is optional, or it's not optional. Then we can show an absence edge, a yellow-orange edge to show, well, there is something in the model, but that has never been implemented. So either it's not required for this project, that makes it obvious, or it was forgotten, it's not finished yet, whatever the reason may be. And if we apply this checking algorithm on this small sample project, we look at the individual dependencies on the left-hand side in the implementation. Here is a dependency from main into the schedule header. Consider this dependency, and we move that using the mapping onto the architecture model and proceed with all the dependencies in this entire system. And in this case, perfect, we find a perfect match. The implementation and the model are perfectly consistent. So no deviation was found. Expected result is all edges are marked in green. That would be the result for this architecture verification here on the right-hand side. And now we come to the topic that we want to discuss. We want to apply this technology to show this property of freedom from interference, so absence of cascading faults via access to memory. And here we want to make it easy for the architect who already has defined the software architecture, and that is he can just edit the original architecture model and add the information to which ASIL are the individual elements in this architecture implemented. And this was done in this example by just adding a stereotype to each of the components, defining the ASIL or the QM level. So just these four were used: QM, ASIL A, ASIL B, ASIL D. It's possible to use others, of course. You can use ASIL B of D or something like that. You can even select your own choice of such stereotypes. Just this subset was used in this example. And then we identify which parts of the architecture model are implemented according to the process depth appropriate for an ASIL A, which parts of the model were implemented according to an ASIL D, and which parts did have standard quality measures for a QM model. And the rest, no, there's one step more that has to be defined. You need to tell the system what are the expected operations that between the different safety levels. So, for example, in this example, we have an ASIL A, and that may have some access to ASIL B. Calls are allowed in this example, or we have some example here. QM may read global variables from all other partitions, so reading global variables is always allowed. Doesn't impact the functional safety of the system. Lower ASIL may call higher ASIL functions if appropriate. If appropriate validation of input values is performed, and lower ASIL may not write to higher ASIL global data. Something like that could be a rule set. This can be adapted. You can basically draw an architecture definition with this different ASIL levels and define which rule set should apply to the interaction between the different safety levels. And now everything else happens automatically. You can use the information given before, the architecture model and the mapping, and simply derive a new architecture model from that information. So transfer or recompute the mapping of this original source code to this partition architecture where only the different safety levels appear. So we find, and if we then run the architecture check, we get a quite different checking result. So there is a deviation from that QM partition to the ASIL B partition because of calls from this application.c, some function inside of the application.c source file, into the directory IO, so some header that is located here. And that causes this red edge, so this divergence of QM accessing into the level B. And there are calls from some source file inside of this CAN driver, apologies, in the other direction, from the com.c receive function to some function that is declared inside of this header, causing this red edge shown here, so that B has an illegal access into the level A. And this illegal access is according to the rule set that was defined in your safety architecture, or in the rules given in this previous slide. So using the architecture check, we can identify in the implementation where is this rule set violated according to the current assignment into different ASIL levels. And what we can also do, can also automatically derive, we can verify the original architecture if this is compliant to the set of safety rules which allowed access from between the different levels. So we can transform the architecture model also in such a partition architecture. There is a QM level, and these are the architecture elements that were marked as QM. So they are allocated here. Those were marked ASIL B, so they are allocated into the level B. And we can evaluate the original permissions giving in the architecture model, and can find out even in the architecture definition there was an error according to the rule set that this access which is allowed according to the architecture is not compliant with the rule set. So you can use your architecture model and verify if that is compliant to the set of rules given for the access between different safety levels. And well, let's talk about how deep this analysis can reach. Is this sufficient to say, well, we have shown freedom from interference, let's abandon all other measures in the development process? And of course, this is a static analysis considering the source code and the architecture model. So it does not address sporadic faults, only the faults implemented in software. So what's it called? It doesn't address sporadic faults, and systematic faults are not addressed. So any fault in the software is a systematic fault because it's a bug in the implementation, and it doesn't. It will always occur given the correct inputs that trigger this bug. So those can obviously not be discovered at this level, and also we have a prerequisite to apply this technology, because we have to make sure that the software implementation is free from unspecified or undefined behavior. So basically, you have to apply measures to ensure that your implementation is consistent. Example, follow the according MISRA rules and ensure absence of unspecified, undefined behavior. And also absence of race conditions, timing issues needs to be addressed by individual static analysis rules. This technology can also be extended to some extent if you consider communication among different elements in the software. If you can identify the corresponding communication partners and can, to some extent, ensure that proper input verification has been done, looking at taint analysis. And, well, to conclude, this is a proposal to ensure at a very early stage in the development that you will not run into a lot of MPU issues during integration of the software system. And it gives some confidence that you have covered this topic, freedom from interference, completely. it's based on an existing architecture model. So if you already have a verification of your architecture in place, it will be very easy to apply this. You just need to add the different safety levels on the architecture to the architecture model on that level, and have to define which interaction between the model elements is appropriate according to your safety concept. And then the rest happens automatically. You can derive the partitions and verify that the communication among the partitions is according to the defined rule set. And then, basically, that's the content of this presentation. Thanks a lot. So this is one technology to ensure this property. Yeah. Any questions?
Open the mic. I was thinking that can you live without that kind of analysis? I mean, in my previous job, I was thinking that we developed software many years, and then we realized that we have to rework. So, is it possible to live without having this?
To live without static analysis? Well, you're required to do to prove that your architecture is appropriate for the safety concept. So basically, you have to do some means of verification of the architecture, and also you have to somewhat show that you have actually implemented your software according to the architecture. So it's better not to live without it. It's better to use this technology to ensure that what you have implemented actually complies to the defined architecture.
That's my understanding as well, so that's why I'm asking. Is there any other questions? There, let me share the microphone.
In your presentations, you mentioned at the beginning that you also should be able to detect, for example, interference because you use the same shared memory, for example. Mm-hmm. Usually, if you just look at the source code, you can easily recognize the calls from one component to the others, but not when you access the same shared memory. Is the tool able to see that you access the same memory? I'm thinking about the VxWorks, for example, where you have just a block of memory that everyone is using, and without really compartmenting them. So is it able to detect that as well?
Yes, we're doing it statically, so there is some. Well, there is some room for false positives in this area. Of course, we detect direct access to global variables quite perfectly. If you're accessing through a pointer, so you're dereferencing a pointer, accessing into memory, there is some, well, you have to make some overestimation of the possible target locations where this pointer may be pointing during runtime, because we do it ahead of time. We don't execute the system, but we compute the set of possible locations accessed through a pointer. But yes, we will detect where this access may go to. And also for arrays, you have to overestimate into which part of an array will this access be going. What will be the possible values for an index into the array. So yes, we will detect if you access the same memory.
Thank you.
Any other? If no, then Steffen,
yep.
Thank you. Great presentation, and